We're going to move on now to Alex Goncharov. So if you could please unshare. Alex will be talking about structure, composition, and transport properties of deep planetary materials at extreme pressure and temperature.
Okay, so I'm going to talk about structure, composition, and transport properties of planetary materials. And what I would like to do today is that, first of all, I would like to tell everybody that, although my scientific view and, my scientific agenda is kind of broader than what I'm going to talk today about, still JCCAS in the last 15 years of my collaboration with them was an essential part of my scientific agenda of my group. And that's partly because of technical developments which JCCAS did over these 15 years I'm collaborating with them. And I would like to stress also is that this is a real collaboration. So, I mean, you talk to these people and you make your suggestion and they listen to you and so on. And if you can, you can contribute in this great box. So I will start today's talk with 4 points how I really, collaborated with JCCAS on the development of various techniques and what kind of results did we get out of that. And then the second part of the talk is I will be actually describing our results in thermal conductivity measurements, where I use JCCAS much less, if I use it at all. And that's something which I would like to do in the past. And a very important point, I think, which I would like to make is that this talk is essentially about how beneficial it is to combine various experimental technique on one sample, something like the theme which we have for almost all users today. Oops, how do I? Okay, so I'll start from first topic which I would like to discuss is combined brilliance spectroscopy XRD primary pressure scale. It's already a number of speakers in this workshop already kind of covered that. What I would like to stress is that really importance of primary pressure scale. So this is the scale which you determine irrespectively of your previous knowledge, essentially, just based on your observations. So what we did in more than 10 years ago, we looked at the cubic covalent materials like silicon carbide and carbon and boron nitride and use them as a primary calibrants and try to determine the high pressure scale. Not only high pressure scale, but we also try to determine a high pressure scale at high temperature. And unfortunately, at that moment, the technique was not developed sufficiently. So we couldn't really get, say, beyond a certain temperature range, say 750 K, and certain pressures like 75 GPa. So our results, in a sense, very trivial. But I mean, the idea is that, again, I understand that, I believe you understand the basic idea. So you measure elastic properties, you construct bulk modulus, and you determine density from X-ray diffraction, and you essentially integrate that, and you determine the equation of state, and you determine the pressure scale. Now, I believe that work nowadays becomes much more important, and the number of speakers already kind of address that. And I think that in the future, we have to do that experiments in diamond anvil cells with laser heating, and I think we close, I mean, experimentally, we are close to perform that kind of experiments. So the second point which I would like to stress is a pulsed laser heating combined with low temperature measurements in addressing synthesis of material with unusual stoichiometry and chemical bond and extreme conditions. So pulsed laser heating, Vitaly already addressed that point in a sense. And I mean, his major point was that you obviously can reach much higher temperature when you do pulsed laser heating. But that's only one part of the story. Okay, so we actually, our development was we quickly realized that, for example, with nanosecond pulses, you can reach very high temperatures beyond 10,000 degrees. But unfortunately, when you look at the temperature distribution and that this is final element calculations, you see that you don't really heat the bulk of the sample, you just heat the surface of the sample. So we realized that it's important to do microsecond pulse heating because this is more comparable in thermal emission, in thermal propagation of the thermal waves. And that in this case, you can see that you can have a thermal temperature distribution very close to continuous heating. So essentially very low temperature drop in the middle of the sample. And we performed this experiment. I mean, we did develop this technique, and we developed the technique of measurements of X-ray diffraction with a microsecond time resolution in a time domain. And this shows you that that we really get a very good time resolution. So you can see that pixar shifts very well with this temperature, and you do this experiment in time domain. So one moment you have a room temperature, another moment you have already quite high temperatures. Okay, so that's unfortunately that's didn't go very far with that, unfortunately. And I would like to, I mean, that in the future, I think we have all potential to extend this workforce, for example, for chemical reactivity and so on. And in my group, you know, we do a lot of experiments with pulsed laser heating combined with optical experiments. And then I will show some of them in the next slides. But at this slide, I would like to show you the importance of this pulsed laser heating with microsecond pulses for synthesis of new materials. Because, okay, in certain cases, you cannot just laser heat materials continuously, or for example, in the presence of hydrogen, because of the diffusion of hydrogen diffuses a diamond cell, it breaks them. So for example, we synthesize high temperature superconductor H3S with a changed composition of hydrogen from elements at, so this is 200K, 203K high temperature superconductor. So at 140 GPa and several hundred and more than 1,000 degrees, we synthesize material H3S. And you see how narrow is the peaks, right? And if you do that kind of things without, sorry. Yeah, I have something here in my home, at my house. So you see how narrow is this peaks and how important is that using that kind of microsecond techniques for that kind of experiments. Another example is synthesis of materials with helium. I mean, you understand that helium is not very likely to form compounds. And what we did, we made the first materials with electrolytes. Electrolytes is a pair of electrons which are taken in the lattice space similar to atoms. So we synthesize that materials again at 150 GPa and several thousand degrees. So I think this is very important, and that kind of experiments nowadays are being used a lot in the material science community, for example, for measurements for synthesis of new superhydrides. Okay, so next I'm going to talk about flat top laser heating experiments combined with time domain spectroradiometry and with respect to in application to melting. I mean, flat top laser heating and so on, this is the bread and butter of essentially X-ray diffraction beamlines, a lot of them, and sector 13, one of those. And of course, you know, they work a lot on determination of the melting curve. And a number of speakers on this workshop already address this issue and trying to determine melting curve, for example, by looking at the diffuse scattering like we did here in the case of platinum. So platinum is a great example of, platinum is a great model or sample because there are good theoretical predictions and also because there are a lot of measurements. So you can kind of address, I mean, you can just kind of clarify your, I mean, your experimental techniques. One of the slides, one of the techniques which have been shown already on this workshop is the work where they use the transmission microscopy to determine the melting curve. But of course, much more beneficial would be to use something which is related directly to the properties of the, I mean, to the melting. And that property is obviously property is obviously latent heat, because latent heat is really, they mow my lawn. I'm really sorry. Okay, so that's here. So I promote the technique which has been developed by Zach Gebhardt, and that actually doesn't include any laser heating. So he essentially makes a kind of breach in the diamond anvil cell, and it passes very short electric current. And if you look at the temperature as a function of time in microsecond time scale, and look at using, in this case, a strict camera to determine temperature. And in this case, it's just a log counts, which you can see. You can determine the melting curve just by observing kind of plateau as a function of time. And if you plot this kind of curve as a function of pressure, you see that it's a really different compared to previous determination. So the reason for that is that, you know, it's different techniques really maybe looking at the different stages of melting. So we need to combine many kind of experiments to really to establish where melting curves are. So that the last point from this part of the talk is going to be on high spatial resolution X-ray diffraction combined with Raman spectroscopy. So I will be talking about in situ determination of the X-ray of the structure of new materials synthesized in the diamond anvil cell. So in that part already has been kind of raised by Leonid. And also, you know, several years ago, I couldn't even think about that kind of experiment. So for example, we were following the mouse experiments with FUO. So we were trying to determine the structure of these materials, of different FUO materials, but we found that not only pyrite structure can be realized, and once you started heating, you see a fence of peaks, and you should just do powder diffraction, and you cannot do that kind of thing. So what is important in this case is a combined various techniques. So one of the techniques, important techniques which we have been developed at JCCAS is Raman spectroscopy. And if you combine Raman spectroscopy and mapping with Raman spectroscopy and X-ray diffraction, you can really determine what is where in different part of your material. But here I show you the result of the laser heat and of sodium azide at 50 GPa. So sodium azide has been thought that it has been thought that it's stable at these conditions, but it appears that when you do laser heating, then the material drastically changes, and you see 3, 4, 5 different materials of different composition in your diamond cell. So when you do, and some of these materials, some part of these materials appear to be single crystal. So if you combine single crystal diffraction in different points and Raman spectroscopy mapping in this, you can determine a lot of information out of this. For example, in this case, Bikov and others determine 2 types of pentazolites, and this has been combined with Raman spectroscopy, which obviously confirm this result. Yet another result, experiments of that kind of, is experiments on carbon-doped H3S compound. This has been appeared to be very interesting part of the investigation just recently 1 year ago, where that kind of material has been reported to be a room temperature superconductor. So in the work which I present here, we determine structure of these materials from at different pressures, just using single crystal diffraction, as you can see here. And what is important is that without that single crystal diffraction, you cannot really determine where positions of the atoms are. except maybe simple structure, which is cubic structure of H3s. However, still determination where hydrogens are remains a very important problem, and it cannot be really done very accurately just if you just do even single crystal X-ray diffraction. Except certain cases, for example, which I would like to show in the next slide, where we look at the novel hydrogen cluster 8 hydride at 1 GPa. And at 1 GPa, as you understand, the sample is much larger, so you can do much better experiments, and you can have much cleaner sample. And here we determine position of hydrogen atoms just from X-ray diffraction, single crystal X-ray diffraction, and these results have been also supported by Raman investigation and theoretical calculation. Okay, so finally, I would like also to mention about iron oxides, and this is the work of Elena Bykova. And Renit was touched on this work yesterday already, and I mean, this is extremely important case to understand that kind of chemistry which happens to these materials, because this is something which is going on, maybe going on in the deep mantle. And what you can see here is that if you do laser heating of FeO, for example, or if you do laser heating of Fe2O3, you can have a materials of various compositions and various structures. And it's of course advantages to have experiments when you do simultaneous X-ray diffraction and laser heating. Okay, so now I'm going to switch to thermal conductivity, and this is something which is, I believe, of interest for this audience. So since a number of speakers already touched on this issue, and I briefly discuss why it is important. But first, I would like to mention that how different is laser heating experiments which we do to determine thermal conductivity compared to the situation in the mantle into the Earth. I mean, important here is that we deal in with a sample of 2 microns thick, and thermal gradients across the samples can be thousands of degrees. And what we have in a mantle, in a, say, boundary layer is changes of the order of several degrees per kilometer. I mean, the difference is huge, and still we are able to determine thermal conductivity of these materials, even in this fantastically, these conditions of very high gradients of temperature. So, I mean, people already described why we care about thermal conductivity a lot. So we essentially have a number of dynamic processes in the Earth's interior, and this is, you see them here, and we're trying to determine them. And one of the key to that is, again, to determine thermal conductivity of minerals and alloys as a function of pressure and temperature. And here I address more on that. So this is just one-dimensional model where you can see, I mean, you have a PREM model which determines the density as a function of density as a function of depth. But to determine how temperature changes and how heat flows changes, so say CMB and so on, you need to know thermal conductivity. And once you know that, you can address questions of cooling rate of the Earth's core, dynamo driving force and its evolution and so on. And that has been already addressed in this meeting. So I would like to talk about experimental techniques which we're using for them, for measurements of alloys and minerals in the diamond anvil cell. And what you can see here in the final element calculation plot here, so we essentially have a slab of material, maybe iron, maybe mineral, and we laser heat it from both sides to get it in a certain temperature of interest. And you can see here the temperature, how does it change with time in microsecond time scale. So you are kind of here, and then you send in a single pulse of the laser from one pulse from one side, and then the temperature on on this heated side increases fast, and then thermal wave propagates across the sample and reaches the sample on the other side with this kind of delay. And by performing thermal final element calculations, you determine final thermal conductivity. And these experiments are being done. The temperature here is being measured by thermoradiometry using a stick camera, and this is an example of that kind of measurement. Seems to be a clean experiment to do, but in reality, in laser heating experiments are quite messy and difficult. So, I mean, that work of Konopka and others has been published in 2016. At the same time, Otter and others, they did experiments on electrical conductivity, and you can see the difference in several times in thermal conductivity of iron. And recent work of Zhang et al., which today are full presented, this is a blue, this is in some way in the middle, and they essentially claim that by combining these electrical experiments and electrical conductivity experiments and theoretical calculations, they kind of made a reconciliation. But the question is, of course, what happens to our experiments? I mean, are they wrong? I mean, are they, what has been done incorrectly? Because we have a number of experiments. One of those I will show you below, which agrees very well with theoretical predictions and other measurements. So the key is, I guess, is to figure out what the thermal conductivity, how the thermal conductivity changes in the function of temperature. So this is the results of essentially Zhang et al., which you see where they show quite moderate change of thermal conductivity with temperature. And our results, I mean, results of Konopka and others, show much stronger results, but we cannot extrapolate that to zero temperature, to 300 K temperature, because accuracy of these results are not very high. So important is to perform that kind of experiments, which we do at lower temperature. But unfortunately, it's difficult for us to do because we have a radiative temperature measurements is our probe, and we cannot really measure below 1500 K. And that's something which I would like to think how to do that kind of experiments with using synchrotron techniques. And I'll describe that in next slides. But before that, I would like to show how much? 1 minute?
1 minute.
Yeah, I'm getting there. So I briefly discuss here about parallelite measurements where we determine thermal conductivity. And this slide essentially is important to understand that the error bars of our experiments are quite high. And we need to make them smaller. And to make them smaller, we need to do a number of things. For example, again, perform low temperature experiments and combine it with other experiments where we can really make a diagnostics of the sample in real time when we do laser heat. For example, we can look at the deformation, we can look at the texture, crystallization of the materials, and we can address the question, for example, about the radiative temperature, which has been raised already in a number of experiments, in a number of talks here. One of the things which I mean is important is radiative thermal conductivity, which I don't have a time to talk about, but important is that it's essentially this is a measurement of the optical properties in very high temperatures, and that kind of technique has been developed in our lab, and Sergei Lavanov's work, which I show you here, which essentially shows you measurements of the absorption spectrum. But once we can measure absorption spectrum, we can measure reflectivity spectrum. And once we can measure reflectivity spectra, we can address the question of wavelength-dependent emissivity, and so we have all this technique in place essentially, so we can address a question of gray body approximation. So essentially, I describe you a number of techniques which have been done already in my lab and using various X-ray diffraction, and other techniques. And what I'm trying to say is that thermal conductivity measurements could be essentially improved if we combine them with the various X-ray techniques. One of the important techniques would be essentially imaging technique, where we can look at the sample simultaneously with our experiments And that's also in other important experiments which we combined can be optical experiments, Raman spectroscopy, but also measurements of the optical properties of the materials. And I thank everyone for listening. Hello.
Thanks, Alex.
Yeah, so I'm done.
Did someone just chime in to ask a question or no? Oh, is that, yeah,
Full.
yes, Afu.
Yes, Alex, thank you so much for the great talk. So you provided an outlook here for with the in situ X-ray imaging. I wonder if you are referring to using this technique to look at the shape and thickness of the sample. And I think the great challenge here is that with the imaging, you probably need to locate the sample. So how do we actually combine such a technique with your proposed methods here?
Well, yeah, sure. I mean, combining these techniques in one experiment would be a challenge. Yeah, definitely. Right. So I'm not very familiar with X-ray microscope techniques, but I guess we are talking now about, in the beginning of that kind of studies in a diamond annular cell. But we already tried a number of experiments in JCCast. So far, we are not very successful. We are trying to determine essentially, to reproduce essentially this flash hidden experiments to determine thermal conductivity of materials. And I think we don't necessarily have to combine that kind of experiments for the same sample, right? So we can do identical loading and do experiments in laser heating, imaging experiment at synchrotron, and continue doing our thermal conductivity experiment in the lab.